Well, hi everyone. My name is Colin Keener. I'm the creator of the COVID Safety for Schools course, and it's a great pleasure to welcome you to this, the third in our series of webinars. This webinar sits alongside the COVID Safety for Schools course, which now includes a comprehensive version and also a shorter 90-minute primer course. Both the full course and the primer are free online resources for school staff and for parents who want to learn more about COVID and how to minimize its impact in schools. The topic for tonight is improving ventilation to reduce the spread of airborne diseases in schools. And in a minute, I'll introduce our presenter, Brad Prezant. We're going to talk about ventilation because COVID is an airborne virus. Like many other viruses, it spreads primarily via inhalation of virus particles that are breathed out by people who have COVID and are infectious. And we also know that infection mostly occurs indoors, which is why COVID has been described as a pandemic of buildings. So in this webinar, we're going to hear about practical steps that schools can take to assess and improve ventilation as a means of reducing the risk of COVID spreading. We're recording this webinar and we'll share it on the website for anyone who wasn't able to join us live tonight. If you have a question, you're welcome to type it in the Zoom Q&A. You'll see a button at the bottom of your Zoom screen, and we'll do our best to leave time for questions at the end of the presentation. Quite a few people have already submitted some questions, so we'll do our best to get through as many of those as well. So I'm delighted to be able to introduce our presenter for tonight, Mr. Brad Prezant from Prezant Environmental. Brad is one of Australia's most experienced ventilation and occupational health consultants. He's a certified occupational hygienist and occupational health scientist, and he has expertise in ventilation and infection control. He advises a wide range of organizations on strategies to minimize infection in the workplace. He's also the author of a comprehensive guidance document on maximizing ventilation in schools, published by the industry body AERA, which is the Australian Institute of Refrigeration, Air Conditioning and Heating. And we'll include a link to that very useful document in the chat somewhere along the way. So Brad, I might hand it over to you to talk for a while and go through your presentation, and then we'll come back and talk some more, answer some questions and answers towards the end.
Great. Thank you, Colin. I appreciate the opportunity to be with you this evening, and for all of you out there. It's my pleasure to talk about this topic. And I'm assuming that you could see my slides at this point.
Yep.
Improving ventilation to reduce spread of airborne diseases in schools. So we're going to start by just reviewing some basics, factors that influence transmission of disease indoors. First of all, not all disease is airborne. There are some organisms that are airborne and of concern, particularly in influenza, measles, and COVID. We also have other mechanisms of transmission that are quite important and generally dominate infection transmission in general, direct transmission and fomite transmission. And I know you all remember at the beginning of the pandemic when it was assumed that COVID was transmitting in this method and we were wiping down things ad nauseum. Unfortunately, that continued for quite a long period of time. But we do know that the major transmission route for COVID is airborne. That was well established. And it's helpful to think in terms of both near field and far field transmission, where near field is when you're within 1 or 2 meters of another person. And far field is when it's over an extended period or extended length away from the source. And it was that recognition that, in fact, COVID is transmitted across long range that was an important distinction, because transmission was occurring not through direct transmission or fomite transmission, but through inhalation in both near field and far field, but sometimes in the far field as well. So when we talk about ventilation, it's important to remember that you cannot manage or reduce near field infection through ventilation. It's just not possible unless you had, like a huge amount of air blowing between you and the person next to you. So the ventilation is always going to be an issue as it pertains to far field exposure. The factors that influence transmission of airborne disease indoors really fall into these 3 categories: characteristics of the virus, characteristics of the building, and personal characteristics of both the person who is exhaling and emitting the virus, as well as the person who is receiving it. So the two key factors pertaining to the virus are, first of all, that the virus is contained within respiratory particulate. We call that an aerosol. And that particulate encompasses a wide range of size. And based upon its size and weight, that will determine how it behaves in terms of settling on surfaces. And once it settles out on a surface, it's no longer airborne. You're no longer able to inhale it. It's no longer infectious in that regard. In addition, just the presence of the virus in the droplet, there's a certain amount of inactivation that goes on that's relatively rapid. So over time, as that virus floats around in a particle, at some point it will simply inactivate in terms of its infection potential. Then there's a number of building factors, and today we're focusing on ventilation. One that's generally not really appreciated very well is the size of the room in which you are, the volume in cubic meters, and that's generally driven by ceiling height. So a standard residential ceiling is maybe 2.7 meters, but you go into a commercial building and it could be 5, 6, 8 meters. It could be a very large space. Large space has large volume. And if you have an infective person exhaling there and you're looking at far field exposures, the dilution is the solution of pollution, as once was said. If you dilute all of that exhaled air in a very, very large volume, the concentration in each breath is much, much less, and the risk is much less. And finally, there's personal factors relative to the generation rate of the person, which is a function of their breathing rate, which is a function of their activity, their speaking. Clearly, if we have multiple infected persons, we're going to have much more infective material in the air. And as far as the susceptible person, the key factor is the dose that they receive, which is the volume they inhale, which could also be driven by activity rate. Someone who is working very hard is inhaling much more volume of air than someone who's at rest, like a student at a desk, as well as the time they spend in that environment. Those two will determine the dose. And of course, whether or not there's any type of protective equipment or masks, either on the infected person or the susceptible person. So those three categories pretty much kind of summarize some of the factors we think about. Just to give you an idea, the variability among these factors is really, really tremendous. This is a study of 11 subjects looking at the exhaled bioaerosol particles between subjects. And you can see that the one on the right, that big, tall blue bar, is over 3,000 particles, whereas there are people who are exhaling less than 100. So this is just a function of our respiratory anatomy, how the air moves through our mucous membranes, et cetera. So you could have many orders of magnitude for some of these factors. And I mentioned ceiling height when I talked about building factors. We're going to focus on ventilation today, but it's really quite interesting to appreciate the importance of ceiling height. This is a 20-minute exposure with a risk of infection for 3 different air changes per hour, which are in that salmon color, the green color, and the blue. So that's 3, 4, and 6 air changes. And then we're looking at different ceiling heights, 3, 4, 6, and 8 meters. And you could see that it's about 4 to 5 times the risk to be in a 3-meter room versus an 8-meter high room. And that's for a 20-minute exposure. This effect becomes much more pronounced as the exposure goes up. So you could see that there's a dramatic difference just on the basis of ceiling height. So both ceiling height, and individual personal characteristics play an enormous role in the risk for any given situation. And I'm sure you all remember this one from the pandemic, where we talked about having multiple mitigation approaches to address all of these different factors. So I'm not going to go into all of this too much. It's pretty much review for all of you, but just to set the stage, let's talk a little bit about ventilation and how it impacts infection. So I'm defining ventilation as the inefficient, and we'll talk about what I mean by inefficient, the inefficient replacement of indoor air with outdoor air. That's what ventilation is. And sometimes people talk of air changes through, for example, a filtration device, which cleans the indoor air. I reserve the term ventilation specific to the replacement of indoor air with outdoor air. And anything else is really recirculation or filtration. So that's an important distinction to make. If you talk ventilation, we're not talking about air coming in from adjacent spaces. We're not talking about air recycled through a filtration device. We're talking about air from the exterior. Again, it can only impact long-range transmission. And whether it's natural or pressure-induced is important because many of our buildings are naturally ventilated, meaning that they have operable windows. But there are pressure differentials that exist in those buildings and do drive air movement. So you open a window, we kind of assume air is coming in that window, but depending upon where that window is located, if you're in a multi-story building and you open a window on the ground floor, the stack effect may actually draw air in that window, which achieves what you're trying to do when you open the window. But if you're on the top floor of a building and you open up a window, the stack effect may actually cause air to flow in at the lowest portion of the building, up through the building, and then exit through that operable open window. So you think you're letting air in from the outside, but actually what you're doing is sucking air from other places in the building through your space, and then it exits there. So natural ventilation or passive ventilation is driven by pressure differentials that can be quite important in terms of how the air moves. When I say pressure-induced, that's just a fancy way of saying a ventilation system or an HVAC system or something like that. Fans are creating pressure differentials. Pressure differentials are creating flows. So we have a fan. We often have sealed ducts. We have some type of supply diffuser, and we have controls. And the most common ventilation systems that we see in Australia are systems that are based upon turbulent mixing of air. So the air is coming in at high velocity. It usually shoots along the ceiling, and it's supposed to induce room air into that fast-moving stream of air, just like a leaf might get sucked into a stream that's running down a mountainside. And that kind of creates turbulent flow and mixing. So that's what we normally think of as an HVAC system. Have we always ventilated to prevent infection? And to what extent has this been on the radar screen? Well, actually, it really hasn't up until the pandemic. We ventilated and have always ventilated for the last 60 or 80 years to reduce body odors, to manage emissions of building materials. So if we have products made from wuzzwood that might contain formaldehyde or other chemical contaminants, the ventilation from the exterior is diluting those contaminants, avoidance of indoor air complaints. And of course, when we do bring in outside air, you hope or want that air to be nice and clean. But we have situations where ventilating with outdoor air may be problematic. For example, if we have bushfire smoke in the outdoor air. But generally, infection prevention has never been on the radar screen for ventilation. This is really something new. Also, the concern about ventilating, focusing on health is also something new. And I think that's a really positive direction that we're beginning to think of the contaminants indoors, how they impact our health, and how ventilation can affect that. We have in Australia a code for building, and we have a standard, which is called AS 1668.2. which basically says for the designers of these buildings, the mechanical engineers who design the buildings, whether it's single-family residential, multifamily residential, commercial, specialty, hospital, school, whatever, there are guidelines for bringing in air from the exterior. And it's called AS 1668.2, and it is what's called a design standard. It's how the building is designed. It governs minimum ventilation for mechanical systems. And generally, it's based on a quantity of air, 10 liters per second per person occupying the space. And there's a big chart in the standard that lists all different types of spaces, the assumed occupancy of that space, the number of persons per square meter or per 100 square meters, and then the quantity of air that must be delivered by design, in theory, to that space. You can also assume a different occupancy if you have reason to believe that to be the case, and then design for that. And then the system is built to that standard. The ducts are sized to bring in that much outside air. The fan is set for that. The cooling system is designed to bring in typically a mixture of return air and outdoor air, and it can manage the thermal demands or the moisture demands that outside air may place on it. So these systems, once they're designed and installed, may not have lots and lots of flexibility. The size of the ducts is predetermined, and it can only take so much air. The system in a very humid environment, say Queensland or NT, you may not be able to pull in that much outdoor moisture and remove it, et cetera. But that's the basic design of the system in terms of its ventilating capacity. Here's typically what you see in the standard. So there's an assumption of net floor area per person. There's a quantity in liters per second per person, and that's the minimum outdoor air flow. We also have a system where if you have a very, very sparsely occupied space, there's only going to be 3 people and it's 600 square meters, whatever. In theory, you're only bringing in 30 liters per second per person, or 30 liters per second in theory, but you can't do that because there's also an area-based minimum, and you have to meet that as well. So you can't fudge this thing with very, very low occupancy to bring in much less outdoor air. But generally, it's the per person one that governs the amount of air. What about naturally ventilated buildings? Well, we have a different philosophy with that. You consider how much the operable window percentage covers relative to the floor area, and it must meet those minimum standards. But there's no validation scheme for the actual functionality of the natural ventilation. So given all of this, let's ask the question, how do schools and Australian classrooms meet this design standard? This is a study that was just published in 2023. It's entitled Evaluation of Ventilation in Australian. It happened to have been Victorian school classrooms. And they used long-term, 1-year indoor CO2 concentration measurements, which gave them a lot of flexibility to do things properly. And I'll talk about some of the pitfalls in measuring CO2 a little bit later. But basically, they concluded that 60% of the classrooms were below the recommended minimum. And you can see on the left the cumulative frequency and the ventilation rate per person. All of the ones that are to the left of 10 liters per second per person didn't meet in practice what that design standard was. So really bad report card in terms of how well these things perform. Of course, the AS 1668 is a design standard. It's not a performance standard. There's no provision for verifying that it actually works. Here's some data that I generated doing a very specialized technical assessment of the air exchange using a tracer gas, which is a very accurate way of doing that. And you could see that these classrooms that I was working on varied from 0.3 to about 0.9 air changes per hour with the windows closed. So a naturally ventilated classroom with windows closed is not really reaching what we would like to see, 3 to 4 to 5 or maybe more air changes per hour. With the windows open, you can get some pretty high values, as you can see in the green colored column. But with windows closed, naturally ventilated rooms are not gonna meet anything near the design standard of 10. Okay, take a commercial building that's very complicated and all of that. Just because we have this design standard, it doesn't mean that the building is operated to that standard. So we actually have no guidance documentation requiring a building to be operated in any minimum ventilation mode. All we really have is the standard for the design. And there's a lot of things that impact how a building actually performs. You could have aging of equipment. All of these dampers are mechanical. There's motors moving arms that are pushing, sheet metal around back and forth. And you can imagine that after 5, 10, 15, 20 years, these things are not going to be operating in the way they were originally intended to operate. So we often end up with structure without function, is how I like to think of it. You know, all the stuff is there that in theory would work, but it's actually not functioning that way. And part of the problem is that, you know, building engineers have always been held accountable for energy use and hot and cold calls. We drive everything with thermal demand. So if no one in the building is complaining about it being too hot or too cold, and the costs are reasonable, those are the KPIs for building engineers. Ventilation or infection prevention have never been on their KPI screen. So all of that would be really new to that community of people. You probably have seen this drawing or something similar to it previously, where we have the susceptible person and the infected person. The infected person is generating those very large purple droplets, which fall out before they reach the susceptible person. And all the small particulate that has the capability of floating around for, you know, 20 minutes, 30 minutes, an hour, whatever, is moving around the room, and the person who's susceptible is inhaling it. We've got multiple sources of outdoor air coming in. In this drawing, I've shown two in blue. One is a natural or fan-induced flow of outdoor air, which is diluting that respiratory aerosol that's contaminated. Plus, we have infiltration through the building. We always have a small amount of infiltration through all the cracks and holes in the building. And then we have exfiltration, which could be natural or fan-induced. When we talk about air changes per hour, and we talk a lot about that, people talk about that, they make recommendations of that. What we're talking about is the flow inward divided by the total volume. So if the flow inward here is 50 liters per second, and we have 200 cubic meters of space in that room, okay, 50 liters per second times 60 seconds in a minute, that gives you 3,000 liters per minute, if you're following my maths. 1,000 liters is a cubic meter. So 3,000 liters per minute is the same as 3 cubic meters. So we have 3 cubic meters per minute flowing in, and over the course of an hour or 60 minutes, that gives us 180 cubic meters coming in per hour. And we know that the volume is 200 cubic meters. Okay, so 180 divided by 200 is 0.9. So we would say that there's 0.9 air changes per hour in this space. So that's where that air change per hour comes from. So do you all follow the maths? Not only is the total flow important and the dilution flow, but directional flow is important as well. So you see the susceptible person who's really located right under the air intake, right? So all that clean air in theory is bathing that susceptible person, and the infected person is close or closer to the exhaust. So in theory, a lot of the infected material wouldn't be going to the left of the infected person. If the airflow is from left to right, it would be flowing out that outlet and minimizing the exposure of the susceptible person. So it's always important to think in terms of the direction of flow as well as the total flow. And I said earlier that we have, or we tend to use in Australia, high velocity mixed air systems where we blow air in through supply diffusers at high speed. It induces room air and makes kind of this like circulation of air that's mixing. That's only one type of ventilation. Another type of ventilation is displacement ventilation. And you could see two examples of it here, where the air is flowing in at much lower velocity at floor level or on the wall very close to floor level. And the thermal plume of the occupants, which is just the heat that we're generating, which is flowing upward, induces that clean, fresh air to go up. And the return air pathway is through the ceiling. So you could see that if we have an infected person and we have a displacement ventilation system, that a lot of the contaminated air that they're exhaling is going to be flowing up and not across to the other individual. So this is one way that we can control the flow of air in new design to minimize risk of infection. For a naturally ventilated building with operable windows, we could also look at the flow of air. And you could see that in the good category, single opening, 2 openings in the same wall, 2 opening with wings. Better if you have 2 openings on adjacent walls. And the best is when you have opposite walls with openings so that you have more of a piston flow of air through the space, perhaps even wind-driven. So, you can manage the control of air potentially even in a naturally ventilated building. Okay, how do we measure ventilation? This concept of outdoor air coming in. Well, the best way is to look at the design intent, and most buildings, certainly most schools, have prints of exactly what are called the mechanical prints that detail what should be and what in theory was put in when the building was new. And I've colored in here some of the supply ducts and some of the supply diffusers. And if you look, you can see that each of those diffusers, I'm not sure if the numbers are going to come through far away, but each of them has its size and the volume of air supposed to be coming out of it. So the one in the center is 30 liters per second. The 2 on the right, my right, are 80 liters per second. And it looks like all of the others are 80 liters per second. The only one in that tea room, that's the glass, is 30 liters per second. So that's, in theory, what should be happening. And you would have a similar drawing for the central system and the outdoor air intake and all of that that would specify what it should be doing. So here's another schematic of what that would look like. The green circle is showing the supply diffusers, and you've got some type of a blower, a fan, and hot water, cold water, whatever, return air from the space. This one doesn't show outdoor air intake, but let's assume there's also some outdoor air flowing in. And that's the basic system that we're looking at. And if you then go in, you could see me in this photo in an office. I'm holding up an instrument that's measuring the flow from that supply diffuser. And now I just read off 56.9 liters per second. So I could compare that with the specification and see whether the system is delivering what it says it's doing. And we could do something very similar to the outdoor intake, air intake, and directly measure the volume that's coming in. And if we think that the occupancy is 30 persons and they're each supposed to get 10 liters per second, then in theory, going into that outdoor air intake is 300 liters per second. And we could test that and validate it. So that's one way that we would do that. We would compare with the original design specs and see whether those measurements are actually being achieved. And then we could have design, initial, what we measured, and that sort of thing in some kind of an accounting throughout the space, comparing those two different measurements. So these type of direct measurements are very accurate, reliable. They certainly could indicate whether or not something has changed since the original system was designed. And we could see that it's operating properly. It does require a little bit of extra effort and expertise, but it's really not a tremendous amount. I mean, I've gone through a rather large CBD building with a technician in one day, doing half of the supply diffusers, comparing it with the original design intent, and of course we did discover some discrepancies. Okay, well, what about measuring carbon dioxide as a proxy? I'm sure you've heard lots and lots of discussion about CO2 monitors and measuring CO2 and trying to use that as a proxy for understanding ventilation. And what's the target? What's good? What's not good? That's an important question. So let's talk a little bit about CO2. CO2 enters from the outdoors. So when I first started practicing in occupational hygiene, which has been a while, the outdoor carbon dioxide levels varied between 325 and 350 parts per million. And of course, with global warming, now outdoor concentrations may very well be 425. That's in one lifetime. But we do have CO2 coming in from the outdoors and infiltrating to buildings. If we had any type of combustion going on, either near the intakes of the building or within the building, we could be producing some carbon dioxide. That's not often the case, but something always to think about. But the main source of CO2 indoors is produced by people, and it's proportional to mass, and it's the mass of the person. So whether we're talking a 5-year-old or a 45-year-old, 100+ kilogram male, we're talking a proportional volume of CO2 being produced from those different mass individuals. It's quite proportional to activity level. The higher activity level, the more CO2 we're producing. And it's also gender associated. So men produce more CO2 than women. If people occupy a space over time, the CO2 levels will gradually increase and reach a steady state value. But that steady state value really varies depending upon the density of occupation and depending upon the air exchange. Okay, so how do we remove CO2? Well, if we pull indoor air out and outdoor air in, we're diluting it. Of course, if we pull air from another space in the building that doesn't have people in it, we would be diluting it. That's not outdoor air ventilation, but it would reduce the CO2. And of course, there could be some type of air cleaning technology that removes the CO2, but that's pretty uncommon. So a good way to think of CO2 is it is the ever-changing dynamic balance between the generation, the removal rate, and the volume of the space. And the best analogy I can think of is a bathtub with water flowing in through the faucet and water simultaneously flowing out through the drain. Okay, and I think intuitively this could help you understand what we're talking about. So the water flowing in is the source strength of carbon dioxide, what we're exhaling. The drain is the ventilation system. That's removing CO2 from the system. And the level of water in the tub is the momentary value of carbon dioxide. So you probably can imagine that if you set the drain just so, and if you set the faucet just so, initially you won't have a whole lot of water in the tub. The level will be kind of close to the bottom. But over time, you might see the level creep up. And it could be that if you tweak them just properly, you can have water flowing in and water flowing out indefinitely. And based upon where you tweak it, you could have the tub very lightly filled. You could have it halfway up the top, or you could have it all the way to the top. All right. So that's a good model for understanding CO2. We're not really concerned with CO2 as a contaminant, as a toxic substance. So what we measure when we measure CO2 in a room or in a building, it's not really reaching a level where it has physiological effects or toxicity. It would have to be well above 5,000 parts per million for it to be affecting us, generally speaking. And of course, CO2 is not any type of a measure of general indoor air quality. It's just a measure of the CO2. We shouldn't take the level to be indicative of indoor air quality. It's strictly related to the exhalation by occupants. So this is what you would see. And in this model, we have 12 children, 23 kilograms each, between 3 and 9 years old, with an activity level of 2 Met in a 100 square meter room with a 3-meter ceiling. This is what you would see in terms of carbon dioxide. So at T equals 0, the levels would be around 425, and it would take 2.5 hours to reach almost 98% of its steady state value, which looks to be around 850, 875, something like that. And it would just rise up in that exponential curve. If the source remains in the space, the CO2 levels will gradually increase and reach a steady state value. But that means that all the people have to remain for 2.5 hours for that to happen. So if occupancy is intermittent, people come and go, it's not gonna do this, okay? Or if they're only there for half hour or an hour, it's not gonna do this. The actual time to steady state depends upon really the drain and the faucet. If there's a lot of people in the space and the faucet and the drain is mostly closed, then it's gonna take quite a while for it to reach that steady state. It could be anywhere between 20 minutes and 8 hours. In an office building, based on 3 persons per 100 square meter, the typical time to reach steady state is 6 hours. In a classroom, which is much more densely occupied, you typically will reach steady state between 1 and 2 hours. And that steady state at a minimum ventilation can range from 1,000 ppm to 2,500 ppm. And that's, again, based upon the mass of the individuals, their activity level, et cetera. So it can be quite variable. I note here, and I think we had a couple of questions about transport vehicles, depending upon whether the windows are open or a ventilation system is operating with the vent open, you could have much higher levels in a vehicle. So I remember, many years ago when I had one of the earliest portable CO2 monitors, and I was going to a job where I needed that monitor. I remember trying to warm it up in the car because back then you had to warm them up. They needed 15, 20 minutes before they would give reasonable readings. And I remember just noticing it was like 2,500 ppm in my car. I was like, oh, wow. Well, of course, I mean, the heat isn't on, the windows are closed, I'm exhaling, so yeah, it could easily be at a level like that. Okay, let's see. All right, so when you measure CO2 matters. So here are some interesting examples. We'll start with an office space. And it takes 6 hours to reach steady state. After 1 hour, you're only going to have an additional 239 parts per million over and above that 425. But if you waited that 6 hours, you'd have an additional 600. At 2 hours, what we're calling T-metric, the level would be about 383 above the 425. But ultimately, that level is going to build to 600 above the 425. Let's look at a classroom of 5 to 8-year-olds. It takes 1.4 hours to reach steady state, and it's just a little over 1,000 ppm, 1,050 or so. But after 1 hour, it's only going to be at 563. So again, at 2 hours, if we use that as the metric, it's going to have reached that steady state. Because of the high occupant density of a classroom, the time it takes to reach steady state is much less because we're ventilating on a per person basis, which means that a lot of air is flowing into that classroom. If we have 30 assumed children and we're having 10 liters per second per person, that's 300 liters per second coming in. Whereas in office space, you have 3 persons per 100 square meters. You only have 30 liters per second flowing in per 100 square meters. So it takes a much longer time because the ventilation rate is much lower. Here's another way of looking at it. The time to steady state is 6 hours, and the time to steady state times the ACH, the air changes per hour, always equals 3. So if you have a very low air exchange of 0.5, you have to multiply by 6 to get 3. But if you have a ventilation rate, of 4 air changes per hour, it only takes 1 point something hours to reach steady state. So you could always figure out, if you know how long it takes, you could almost kind of infer the air changes per hour and the ventilation rate. So what this says is that if you have a poorly ventilated space, and certainly many naturally ventilated classrooms have poorly ventilated spaces, they may be down in the 0.2 or 0.3 air change per hour rate. If you measure at 3 hours after of continuous occupancy, which rarely occurs, right? But if you would keep the same number of people there for 3 hours and you looked at that CO2 value and you assumed it was the steady state value, this shows the magnitude of your error in estimating the air changes per hour. So the lower the levels are, when you get down to the 0.2 or 0.3, you have 70 to 122% error in your calculation. So it's critical when you measure CO2 and that the occupancy remains standard for that period of time. This is what CO2 levels typically look like. And what you're looking at in the blue is you're looking at the CO2 level, and the gray is simply the occupancy numbers. So on the right, hand side is the occupancy scale. On the left-hand side is the CO2. And this is real data from a typical classroom where the kids may be in there for 45 minutes and then they all leave. So you could see that sawtooth pattern going on repeatedly. And you could also see that the curve is going up, but it never actually reaches the steady state value because the kids all leave after 45 minutes. There's just that slight lag time that you see in the difference between the occupancy and the levels of CO2. So here, when you look at the number of people in the space, okay, each of those curves represents somewhere between 2 and 7 persons per 100 square meters. What we've done is we've set the air exchange rate to be 0.37 for all of these situations. And you could see that if the space is not fully occupied, if it's partially occupied, you never get very high CO2 levels, right? So not only do you have to wait a long time to measure the CO2 and get meaningful data, but you also have to make sure that the space is occupied to the standard of what AS 1668.2 assumes to be the occupancy of that space. And of course, that makes sense because less people, less exhalation, less source strength of CO2. The momentary CO2 is the dynamic balance between the source strength and the removal rate. You have a very low source strength, you don't get a very high level of CO2. So measuring the same classroom, for example, at 2 hours, you could get anywhere from 500 to 900 ppm of CO2 based upon the number of people there. So the number of people is just as important as when you measure. Okay, and it's proportional to mass and activity level. I think we'll leave this equation, but the production of CO2 is a function of the two. Just to show you how that impacts, here are 2 different examples, and we're taking some very small female children of 23 kilograms each, between 3 and 9 years of age, at a MET activity level of 2, and the generation rate for each of them per person is 0.0042, and the steady state CO2 concentration in a room with ventilation fixed would be 843 parts per million. But now look, if we use males, okay, who are normally, like adult males, a little bit more activity level, that's 3 times the generation rate, okay? 2.9 times the generation rate. And the steady state CO2 concentration in the exact same room, the exact same ventilation is going to be double. And if those males are banging on drums or something, it's going to be double that again. So the activity level and the mass really do have a big impact on what the steady state level is. And if you were just measuring CO2 and attempting to infer the ventilation rate, all of them have the exact same ventilation rate. Okay, if you don't pay attention to the mass and the activity level, again, you could be making some pretty erroneous conclusions. That even operates in a difference between younger and older children. So let's talk about CO2 testing then in terms of its reliability. What we would love to see is what you see here. On the left, we have actual negative or positive, and on the right, we have predicted negative positive. So you could think of this as a pregnancy test, okay? Let's say you take a pregnancy test and you're not pregnant, and the test tells you you're not pregnant. That would be a negative. And you want that to be really high, right? I mean, you don't want it to tell you you're pregnant when you're not more than 1% of the time. So we have those 1% in that predicted positive column, but actual row is negative. So you're really not pregnant, but the test is telling you 1 out of 100 times that you're pregnant when you're really not, okay? And then if you are pregnant, okay, you want the test to confirm that 99% of the time. So these are the kinds of numbers that people would generally find acceptable, a 1 in 100 error rate for a pregnancy test. But when you do the same type of a test for carbon dioxide, okay, let's look at the reality versus the prediction. And let's start by talking about false positives. So you do a test and The reality is that the space is well ventilated, but you have really high CO2 values, okay? That's the case where you might have a bunch of very large men running around banging drums. That doesn't happen very often when you're measuring CO2, but that would be an example of a false positive, and that's not a real common thing, right? What about a true positive? The space is poorly ventilated and you're measuring 2,500 ppm. This is really the best thing that CO2 monitors and measuring instantaneous levels of CO2 have going for it. So you walk into a space and the levels are egregiously high, 2,500 ppm or something like that. This is a true positive, okay? You know that there's probably no ventilation whatsoever. So that's really the low-hanging fruit. So you go into any type of a building, you look at a bunch of different rooms, and some of them are really high CO2 levels, then I think we could safely conclude that these are really spaces that have issues with outdoor air ventilation and replacement of the outdoor air. What about the true negatives, where the space is well ventilated and we get a low CO2 value? Okay, that's great. We're happy with that. The problem is these false negatives, okay? Where the space is poorly ventilated, but we didn't wait long enough to reach steady state, or we had very small people there not doing much. Those are false negatives. And I think that's where the concern is. You go in and after an hour, when steady state is going to take 4 or 5 hours to be achieved. And, you know, we have a problem there. Okay, so what can we learn from testing for CO2? Very high CO2 levels are generally true positives, and if they signal ventilation is poor for the given occupancy, but moderate CO2 levels can be false negatives. Either the room wasn't at maximum occupancy, the children were sleeping, or you didn't wait long enough to reach steady state. So you really have to pay attention to all of the conditions when you're attempting to use CO2 to infer ventilation. So CO2 is influenced by the assumed occupancy. It must remain consistent and at maximum throughout the measurement period. It can be a useful index of or a proxy of ventilation only when the factors influencing the steady state assumptions are taken into consideration. A better result absent false negatives may be to use the concentration decay model rather than the constant injection model. I'm not going to go into this now, but I have a slide at the end of my talk. And I know we had a question about doing concentration decay, but we'll leave that for further elaboration. And finally, other tracer gases than CO2 may provide better measures of air change per hour and ventilation. And that's generally how I measure ventilation, is with a different tracer gas. Okay, so let's talk about mitigating transmission via filtration or inactivation as opposed to dilution, which is what ventilation is. Respiratory droplets can be filtered out or they can be inactivated, and the filtration can be mechanical or the inactivation can be done by a number of different methods. And one little caveat here is that some of those methods may create undesirable byproducts. So it's really critical to be an astute consumer of inactivation methods to make sure that we're not producing things that we really don't want to have in the indoor environment. Okay, there is a structured approach to infection control that was recently published last year by the American Society of Heating, Refrigeration, and Air Conditioning Engineers. I was on this committee. I think I was the only Australian on this committee. It was mostly Americans, but there were people from Europe and Asia as well. And what ASHRAE sought to do was provide a structured framework for minimizing infection control that was risk-based. So the goal of ASHRAE 241 was to establish minimum requirements for the control of infectious aerosol to reduce risk of disease transmission. And the way that it was done is that all of the contributing factors would be considered, and an equivalent clean airflow was established as if it were outdoor ventilation. So what that means is that when you filter the air and remove the respiratory particulate, you can calculate what the equivalent amount of outdoor air coming in would be as it moves through that filter and takes out the particulate. So here's a chart from that. This is what's called minimum equivalent clean airflow per person. And if you look at classrooms under educational facilities, you could see that this risk assessment, which is equalized across all of these occupancies, requires 20 liters per second per person of clean air that's either outdoor air or filtered air or inactivated air. Okay, so that's basically double what the minimum standards are. So if you can achieve 20 liters per second per person, let's say you have the ability to increase the ventilation to double it from that minimum, or maybe it's even at that right now, then you would have less than a 1% chance of infection in a 1 hour period. And based on all of these different occupancies, they have different equivalent clean airflows. So if you look at gyms, assuming you could see these small numbers, it's 40. So it's double in a gym. And the reason for that is that people are both inhaling much faster and more volume of air, and they're emitting much more. So you need double the amount of equivalent clean air. So this is a great system for a structured approach to infection control management. And this is just a schematic from the standard, which basically shows you that the thing that's circled is the mechanical ventilation system that already exists. It has outdoor air, it has relief air, it has return air from all different zones of the building, and it's delivering it to the space. But then they have all these other air cleaning systems, and they could be HEPA-type filters, or they could be some inactivation system or something like that. The one next to the people is a portable air cleaner, but you could have air cleaners that are mounted in the ceiling for a particular zone or for a particular room. And what the standard says is that all of these added up together are what determine the equivalent clean airflow. It's the sum of all of these different things. Okay, so let's talk about some of those things that you might employ and use. Air-to-air heat exchangers, where outdoor air is brought in, but it's heated or cooled from the indoor air that's being exhausted. Central room filtration, some type of system like that. Central room inactivation, where you're not necessarily filtering the air, but you're inactivating the virus. Portable filtration, which I think you're all familiar with. And there's this University of Melbourne chart that looks at the air changes per hour provided by the different manufacturers and the cost of that. That's kind of a nice resource. And then there are other technologies, including ionization, photochemical ionization, and bipolar ionization, where we're a little concerned about the contaminants that may come out the other side. So while some of these air cleaners have both filters and certain types of irradiation or oxidation technology, one needs to be quite careful about the contaminants produced. And we even have these things, which, if you've heard of them, they work extremely well. They're low cost, what are called Corsi-Rosenthal boxes, which are portable homemade filtration, where we take a bunch of filters and a fan, and we basically tape them all together with duct tape. They actually work really well. And then there's ultraviolet, and there's two different types. There's the kind that has to go in the upper part of the room with louvers because you can't have your eyes or skin exposed to them. And there's another kind that could be in the occupied zone, and you could basically be bathing in it in terms of your eyes and skin. That latter type has the ability to create some oxidants and may have some issues with it. Still under investigation. Okay, let's summarize what we've talked about today, because we're getting close to the end. Far-field airborne transmission as one mechanism of transmission can be assessed and managed through a variety of approaches. Ventilation is one mitigation strategy. Measuring ventilation is tricky, particularly when we try and use CO2 as a proxy. We have ASHRAE 241, which is a structured approach to a risk-based approach to combine multiple cleaning technologies with outdoor air ventilation to achieve an equivalent clean airflow to achieve a quantitative risk target. So the idea here is that many systems may not be able to simply double the outdoor air intake, but we can achieve the equivalent clean air by these various cleaning technologies all summed together. And finally, thank you for your attention, and we'll take questions.
Thanks, Brad. We've covered a lot there. Um, I'm going to start with a question that was posted in the lead up to the webinar, and it's a common one that comes up from parents and teachers, and it's about the use of CO2 monitors where it's either being brought along to the classroom by a student or by a teacher. Does it need to be placed in a particular location? Can it be in the occupant's pocket? Should it be in on a desk? What's a good location to get, notwithstanding the limitations of CO2 monitoring that you mentioned? What's a good way to make sure that you're actually getting a reliable, meaningful result?
Yeah, I mean, I think reality is that where you place it in the room is going to give you a very variable reading. So if you place it somewhere where it's being influenced by the incoming air supply, then you're going to have a much lower value than if it's someplace that's quote unquote a dead zone. And the placement of the diffusers, the velocity of the incoming air may determine whether you're in a very well ventilated area or a dead zone. So there is no perfect place for every room. Some studies that have been done place the CO2 monitor at the exhaust of the room, but that may actually just be an average of what's going on in the room. So there may be hot spots and cold spots. So that's really one of the weaknesses of a CO2 monitor, is that where it's placed in the room is going to have a significant effect on the reading. There is no ideal spot. It's going to depend upon each room and the pattern of flow.
Sure. So related to that, I have a question here from someone who's noted that their school thinks that it's okay to measure the CO2 levels once for each classroom. I think you've talked about this, but are there any other, or in your experience, have you seen schools doing this where they measure the CO2 levels on one occasion and say, right, we now know what the ventilation is for that particular classroom?
Yeah, I think that's a common mistake. And the reason that I spent so much time talking about the pitfalls of CO2 monitoring is to bring out that you can't just do a single measurement at a single point in time. If you do a survey of a school where you walk into every classroom and in the course of an hour and a half, you've covered every room in the space and you've written down the value, that's reasonably meaningless, except for the classrooms you walk in and the levels of 2,500. So that's a pretty good first cut at where your worst areas might be, and it could be a prioritization schedule for where you would intervene to try and address the concerns. But you may only find 30% of the problem spaces that way, because you only get 30% true positives and you're getting 70% false negatives. So I try to address that in the context of the talk, because I do think it's important that people realize that CO2 can be quite useful, but you really have to consider all of the factors that go into its value. And where it's most useful is when you're continuously monitoring a space over an extended period of time. So that study that I cited, they actually measured for an entire year continuous CO2 values for that entire period and drew conclusions based upon that.
Sure. Someone else has asked about buses and accommodation for school camps. What's your experience in dealing with ventilation on coach-style buses, which typically haven't got openable windows?
Yeah, there actually have been some studies on that. Depending upon the bus and how the system is turned on or off, it could be well ventilated or it could not be well ventilated. So it really depends upon it. Most aircraft, for example, are extremely well ventilated. The problem in an aircraft is that when you board and leave, you're all standing in the aisle breathing into each other's faces. So when you're actually sitting and the systems are operating, you're getting really good ventilation. Some buses have good ventilation, some have really poor ventilation. Clearly, if you could open the windows, that's going to improve the ventilation dramatically. But it's impossible to predict until you actually go into the bus and see.
Yeah, I think you've probably seen, as I have, some CO2 charts from school buses where they've got up to the between 5 and 10,000 parts per million. So back to your true positives comment,
Yeah.
I think that tells us a fair amount. I have another question here from someone who's asking whether there's any merit in having a ventilation standard that's based on a hybrid mechanical and natural ventilation system, where you've got the mechanical ventilation controlled by some kind of CO2 monitoring. Is that something that makes sense or that you've seen used?
Well, CO2 monitoring or occupancy sensing in some other fashion are actually reasonably commonly used. It's termed demand control ventilation. And basically, it's a way of sensing when air, not just outside air, but often total airflow, cooling capacity is directed into a room. So if you have a conference room, for example, in a CBD building, and you have a sensor on the wall that measures carbon dioxide and temperature. If that sensor suddenly starts going up in terms of the CO2 values and the temperature starts going up, the temperature may lag the CO2. The first thing that goes up may be the CO2. If suddenly 8 people enter the room, then that's an indicator to the ventilation system that they need to open up the damper with the total flow into that room to address the cooling. And presumably also to properly ventilate for the number of people present. So demand control ventilation is quite common as an energy saving strategy, because then when those people leave the room, the system is going to be closed down, the amount of air flow total, which determines the energy usage. It's expensive to move air. Air actually weighs something. It's hard for people to appreciate that, but moving air around is an expensive proposition. So if you could reduce the flow in that system by measuring the CO2, then that's a technology that's often utilized. So does it make sense? Potentially. It makes sense. You do want to ventilate when the spaces are occupied and perhaps not ventilate or direct the ventilation somewhere else and the airflow somewhere else where people are present. I think when you measure CO2 in the air, that's really not the most precise measurement of occupancy. I wouldn't be surprised if someday we have some type of a camera video-based system and an AI-based system that detects not only if people are present, but their mass, their activity level, and turns that into some type of a index that can be used to properly ventilate the space. I think we're moving in that direction.
We have another question here about air purifiers in classrooms. What's your experience in terms of giving schools guidance on how to choose the right air purifier and to have the right number and the right placement so that they're actually doing the job that you need them to do?
Yeah, that's a good question. Placement, obviously, if you knew where the infected person was, you'd put the intake of the cleaner close to the infected person. And you would put the outlet of the cleaner towards the susceptible person. So clearly you wouldn't want to site the outlet so that it's pointing towards the exhaust in the room, right? Because then all your clean air is leaving. You would very much want the clean air to go towards where the people are. It turns out that a lot of portable units, they don't separate the exhaust air, the clean exhaust air, and the intake air so well. So if you might get lots of re-entrainment. So you'd have clean air that's going out of the unit, and then that clean air is then going back through the unit and getting recleaned, which is kind of a waste. So if you had, for example, an exhaust on the top of the unit that directed the clean air upward and outward, then you might have very little re-entrainment of that clean air back through the unit again, and it's going to work at a much higher efficiency. So I've seen some studies that suggest that many of these units operate only at about 75, 80% efficiency. So 20% of the air they're pulling through has already been cleaned and is clean. So that's kind of a waste of energy, it's a waste of opportunity, and it's noise without value. So the design of those systems, the exact design is important to minimize that re-entrainment. The ASHRAE 241, if you follow the guidance value for 40 liters per second per person, and you have, let's say you're only getting 5 liters per second per person in the ventilation system, then you need the supplemental filtration to make up that other 35 liters per second per person. And then you would size your units, the number of units and the capacity of the units to achieve that value. So you take your assumed occupancy of 30, say, and you take your value of 35 and you multiply one by the other, and then that's your total air cleaner, clean air delivery rate, really. And it may take 2, it may take 3, or it may take 4 units of different size to achieve that OSHRA 241 equivalent clean airflow standard.
Just to add to that, if anyone's had a look at the Clean Air Stars website, it's got a useful tool for searching for air purifiers. It actually provides the air changes per hour at different fan speed settings, so you can actually work out and compare units using that tool. So it's kind of handy. We've had quite a few questions from people asking, which I guess is the key question in all of this, is how do we get schools to act on this stuff? So we can sit here and talk about air changes per hour and CO2 levels and all manner of stuff, but the biggest challenge that we have in Australia and worldwide is that schools, for the most part, aren't doing this stuff. So what magic solution do you have for schools? And I know there isn't one.
Well,
let's spend a minute talking about like how can we get schools
yeah.
to take this more seriously and to take an interest in using ventilation and air cleaning for improving safety.
Well, no magic bullet, but some ideas. So when I audit schools, hospitals, AS6 100 headquarters, that really doesn't matter what the building is. Very often I find deficiencies that not only might compromise indoor air quality, but are costing money. So very often there is a solution that both improves indoor air quality and saves money. So there's this low-hanging fruit of energy efficiency that you can gain simply by investigating. Not always, but often. So sometimes there's that silver lining. In addition to which, there's probably pretty good evidence, there is pretty good evidence that the performance of students and all persons improves with better air quality and degrades with poor air quality. So there's a connection there between the efficiency of education and the quality of air. So obviously we would want to, for all your invested effort, you'd want to maximize your quality of education. And having kids fall asleep because it's the levels of indoor air quality is so poor that they can't concentrate is no bargain, right? So that's another factor that might help. And there's quite a few studies that have been published on that, on student performance and better air quality. So those are 2 thoughts and ideas.
Thanks for that. Another question about CO2 monitors. A question here, which is, I think, basically asking how long does it take for a CO2 monitor to give you an accurate reading when you enter a room? So if you walk into, whether it's a classroom or a restaurant, whatever it might be, and you have a CO2 monitor, how long do you need to be in that environment to be able to say, right, what I'm reading is actually representative of the CO2 levels, and then, make some kind of rough assessment of what that means for ventilation?
Well, we already said that it may not be whatever the reading is, however long you wait before you look at the screen, it may not be representative of all the locations in the room. Okay, so let's start with that you're measuring one point in time, one place, and if you went to a different place in the room, you might measure something quite different. You've got that issue. Most of these systems, depending upon their design and quality, are going to measure within a minute or 2 what they actually think it is. In other words, you'll reach some steady state value on the instrument. The instrument will be consistently reading the same value. And that's really a function of, most of them are passive. They don't have fans. They're not drawing the air through. So it takes a certain amount of time for the air in the room to diffuse into the instrument and for stable reading to occur. And that may only be a minute or 2. Couple of minutes. So generally, it's not a long period of time before you get a stable reading. The problem is making sense of that reading. The fact that where you are in the room is going to be variable, and the fact that all the things I talked about, how long it's been occupied, how many people have been there, whether you're developed, you're getting good data out of that to draw whatever conclusion you want. relative to the ventilation. But the issue really isn't the time it takes for the unit to read.
Sure. Um, a lot of questions about CO2 monitors. So here's another one from someone who says in their school there is a CO2 monitor set to turn on a light at 1200 ppm, and this should trigger the teacher to open a window and turn on a fan and turn it off when it gets back down to 1000 ppm. The school feels this is sufficient and not interested in any other action. How can we challenge them that this is not enough?
Well, that's not a bad idea to have the CO2 monitor turn on a light and remind everyone that you might have to open the windows or do something to increase the ventilation. 1200 ppm, you could have, if it's after 15 minutes, you could have a really poorly ventilated space. So taking those actions is quite useful. The alternative, which is no CO2 monitor and no light and no mitigation, seems pretty awful by comparison, right? So it does seem good. So the question then becomes, well, what concentration do you set it at? Do you set it at 1200? Do you set it at 1000? Do you set it at 800? I think that's the more relevant argument. If you've got a classroom, the issue is probably not what number it is, but the rate at which it's increasing. If it's increasing really rapidly, then you probably have very poor ventilation, and there's no point waiting until it reaches 1200 to realize that and do something about it, because if you do whatever you do about it, it's not going to suddenly drop down from 1200. It's going to take time for whatever that effort at increasing the ventilation might be for it to impact. So you're going to spend a long time in the poorly ventilated zone, is what I'm saying. So getting a much more early warning system that, for example, detects the rate at which it's increasing would be a lot more valuable than simply waiting till it gets to something that's clearly a problem.
Yeah. And I guess the other observation I'd probably make is that, a lot of schools, both principals and teachers, are not well informed about the why, why we should care about ventilation or the health risks associated with not just COVID but other viruses. So I think there's an information gap there that I think some schools are starting to address, but I'd probably make the observation that that's still lacking in terms of that as a driver for schools to
That's the
take
approach.
action.
Yeah,
Yeah.
it's a good start, but
Yeah.
not the best approach.
Yeah, I'm conscious of time. I think we probably should wrap it up. I just wanted to also, I will put in the chat for this webinar a link to the excellent document that you wrote and that's been published by ERA that goes into some of these topics in a bit of detail. I'll also put a link to that on the website. For anyone who's done the COVID Safety for Schools course, you'll already be familiar with it. It's linked in there in the module on ventilation. So I think we'll wrap it up. Brad, I just wanted to say thanks for your time and expertise. It's been incredibly valuable. We've covered a lot. I'm sure there's a lot of things that we could go into in more detail, but that'll be for another time. I'd also like to encourage anyone who hasn't yet done either the full course or the primer, the 90-minute version of the course. To do those, you can register on the website, covidsafetyforschools.org. They're entirely free and have now been completed by over 1,000 school staff and parents and counting. So thank you everyone for being here. Thanks again, Brad, and we'll look forward to talking some more about some of these topics at a future session.
Thank you, Colin.